Hello, guys. Welcome back to the Astroimaging channel. Tonight's session, presented by David Alt, is image selection. He's going to go into a little bit of which images to, or I should say, which subframes to use and which ones to throw away, or which ones to do something in between. But as always, before we go into that, I'm going to share my screen and show off this week's image of the week, which goes to Christopher Massa for his Jones Emerson 1. A very cool image that you can catch on our website, theastroimagingchannel.com. And at the same time, you can submit for your own. And I do want to mention on our website, you can always go in and comment on these images. So far, we don't get many comments, but we do get lots of spam. I don't know why. Complimenting me on how nice my article was, which is funny because I don't write any articles. Yeah, so if you have a chance, submit. Lots of great images. Actually, the other thing I wanted to mention is if you just want to see a bunch of great images, go to Image of the Week submission, and you get to see every image that was submitted for the week. You can star it. You can comment on it. What I mention is if you just want to see a bunch of great images, go to Image of the Week submission. There we go. Okay. Sorry about that, but yeah, so check out our website. Lots of cool stuff on there. I am going to take my screen back if I can figure this out. And yes, there we go. And I'm going to hand it over to David.
All right, thanks, Adam.
No problem.
All right, let me start my screen sharing here. All right, and all right, can you see that, Adam?
Yep.
All right, good to go. All right, so there was a little confusion. This is, image selection, talking about tossing subframes, not about, choosing targets and that sort of thing. So we'll clarify that, in the titles to make sure the searching is a little bit easier to find this. But so what I want to talk about tonight is kind of my philosophy on how I toss images or don't toss images, or what I do with the stuff that I keep. That actually goes into making the final stacks, and kind of what all the trade-offs for those sort of things are. I tend to be very algorithmic in nature. I highly scrutinize my data, but the trade-offs for that kind of effort is typically only going to yield very small improvements. So my data tends to be pretty consistent, and so there's not a lot of differences in the data set. And so when I do this sort of thing and really scrutinize the data, I'll get 2% improvement in star sizes full width half maximum, or maybe a slight decrease in signal to noise ratio to get that resolution, maybe 5%, sometimes as much as 10%, but usually not that big of a difference. I'm generally willing to sacrifice some signal to noise ratio for resolution, knowing that I can take more data to regain the signal to noise ratio if I need to. When you're doing your data evaluation, it's kind of really dependent upon the quality of your data. So if you end up with highly variant data, maybe you have data from different sites, or you're combining data from different people or things like this, then you really need a lot more scrutiny. There's a bigger difference and a larger gain you can get from potentially tossing subs or weighting data or things like this. But if your data tends to be pretty consistent, you won't see as much of a benefit. Occasionally, you'll find scenarios where you do all this evaluating and everything and selecting images, and the result doesn't actually improve. Sometimes it can actually get a little worse, right? Where you didn't see a benefit in resolution, but you lost signal to noise ratio, right? So that can happen. You just need to pay attention to it and kind of check those things out, right? So generally, my process looks something like this. I'll do a visual inspection. I use PixInsight most of the time, so I'll use the blink tool, which allows you to just kind of step through all your images, and we'll toss bad frames if it seems appropriate. Then I do subframe selector to further evaluate whatever was kept from the visual inspection, and then weight that data, and then I register the data and then integrate it with the weighted information. So that gets me, and the weighting allows you to kind of shift where you want the focus of your result. Do you want the focus on signal to noise ratio, which turns more to the defaults of what the integration tool is going to do anyway? Or do you really want it more focused on resolution, where you want to focus on full with half maximum or something like that, right? For complex projects, this tends to be things like collaborations, things like that, where you have a lot of very, very disparate data. It can be really complex, right? So a lot of times I'll register the calibrated data up front and do all the evaluation based off of that registered data. I'll do background corrected on all the subs and everything to make sure that they're all even, fit the data so that everything matches in terms of intensities. And then I actually start with all the inspection and everything, doing the blink, subframe selector to generate my metrics. I'll actually do stuff in spreadsheet form and then translate that data back into, into the fits headers for later use. And then, once I've translated all that and reapplied all my fitting solutions to the original subframes, then I re-register and integrate, right? So it can get really complex if you want it to, and in some cases that's useful. 99% of the time, it's really not. Just making sure you've excluded, whatever really bad frames covers a very, very good portion of it. So why do you limit, or weight images when we're stacking? There's some common things that occur. If you have tracking issues, maybe you had a really gusty night or something, you see some bad tracking, pushing the scope around, or maybe you're having a gearing problem or something like that with your mount. These can show up as regular star shapes. They can sometimes show up as double images where you see the stars in there twice everywhere. Those sorts of things can really affect the final result. And actually, it makes it worse for evaluating the images as well, right? The automated tools do not do good jobs of handling the images whenever there's high elongation or double stars or things like that, right? So it's in your best interest to kind of toss those things out up front, unless you just really don't have the data to do that with. Seeing is another big effect, right? So if you image over multiple nights and you get one night where the seeing was just really poor, you'll get all these bloated stars, and they'll reduce the overall resolution in your final stack. So you really want to exclude those or weight them or something like that to make sure they're not contributing as much and ruining the final resolution of your image. Rejection can sometimes deal with some of those things, right? So if you just throw everything into your stacking tool and allow the automated rejection to deal with those significant differences in star size, sometimes you can get pretty good results, but you can also sometimes get artifacts around the stars, which we'll talk about. Another problem is transparency or light pollution effects. For example, I have some stacks where I've gone to a dark site and collected some data, and then I do some more from my backyard. I have all the time in the world to do it from my backyard, so I can collect a lot of data there. But when you start combining these things, the weighting tools and the algorithms that do the weighting tend to not be able to account for enough of the difference to really affect the signal to noise ratio correctly, to really make sure things weight appropriately for their true signal to noise ratio. And so what ends up happening is your light polluted frames drag down the overall signal to noise ratio of your final stack. This is definitely exhibited in projects I've done, in collaborations I've done, where you get one frame from one guy who's like Eric, who's got a mountaintop observatory. His data is really, really good, and when you combine it with other things, it only just degrades his image, right? So you have to kind of take these things into account whenever you're doing these. And again, I'll reiterate, the benefits here, depending on your data, may be great or they may not, right? It's entirely dependent on your own data set. So before we actually get into some of the issues here, do you have any questions yet, Adam?
There are no questions yet.
All right. So let's talk about some of the effects on your final stacks. So bad star shapes are a pretty common one. So what we're seeing here is a stack of 12 images. One of the images is with all images combined, and one is with a few frames tossed out of the stack, right? Specifically, the ones I defined as being too bad to include. And you know, there were mostly most of the frames had some oblong stars. It wasn't the best stack for this, but you know, there were some that were better. So I included some of them, tossed some of the others. And then what you can see here is I'm measuring the stars and their eccentricity and everything. And there's clearly, in the one where I just combined everything, a few issues. So you can see this this star down here, and it's got a little notch in it, right? So this is one of the issues you can sometimes see when you include, you know, this particular image had a lot of elongation in that star. It extended out. It got rejected, but now you have a lower signal-to-noise ratio in that spot, so you end up with potentially these darker areas. Sometimes you can see them as halos around the stars, things like this. Sometimes it combines fine, and you can just use it as is. But these are things to pay attention to, that potentially tossing a sub or two could actually improve your result, right? The stars are also a little bit rounder because I tossed some of the elongated subs. It's a little hard to see in this picture. You can kind of see in the measurements, though, in the all frames, the R value, which is the ratio of X to Y in the star size measurement. These numbers are smaller, meaning they're further away from round than these numbers, right? So they're a little more eccentric, and it is sometimes noticeable, sometimes it's not, right? There is also a small increase in noise by doing this. I tossed enough subs out of this stack that, you know, I didn't have as much data, right? So my signal-to-noise ratio is going to be lower. So there was a slight noise increase, but overall I preferred the result of dropping a couple frames in this particular one. So seeing or anything that really bloats your stars can definitely have a sizable effect depending on your data. You know, periods of bad searing can degrade the final resolution. You know, typically what this looks like is a blurring. So you can see these two frames here. So in the upper right, you have a stack where I tossed a couple frames. The lower left is where I didn't. You can see it's definitely blurred in the lower left. This one was pretty bad. I had a fair amount of data that was blurrier for this stack, and I only took the subs that, you know, didn't have this. Now in this case, some of it was due to seeing on particular nights, and some of it was due to focus issues where the focus was slipping, and you could actually see it, you know, slip a little bit, and, you know, suddenly the next frame would have, you know, some really bloated stars on it, right? You can tell just from the pictures that the frame on the right is quite a bit noisier than the frame on the left, but it's also a lot cleaner. It's much sharper. Features on here, like you can tell, this is a multi-lobed structure here, and here it's just kind of a blob. There's a distinct star, you know, core to the galaxy here, but it's just kind of slightly brighter here. So there's a clear advantage in this particular example. If you're dealing with anything where you have really high signal-to-noise ratio or low, you know, and low signal-to-noise ratio in the same stack, we talked about this a little bit, but that combination tends to not work very well. So here we have a pretty clear example. So these have been fit, so they're exactly the same intensities, and you can see that the just 11, you know, 10-minute frames from a dark site are significantly better than combining those 11 by 600 with 96 90-second frames from my backyard from a light polluted site. you can see they actually degrade the final stack fairly significantly. So there's benefits and drawbacks here and ways to deal with this. There are multiple ways to limit images or weight images when you're dealing with this stuff. The first one we'll talk about is visual inspection. There's some very good benefits to this, right? Humans are very good at identifying strong outliers. It's pretty clear if you're stepping through a bunch of images, well, it suddenly got, really bright and I don't see a lot of contrast in the image, maybe a cloud passed through or something like that. Or, hey, all of a sudden these stars are really huge, right? We're pretty good at evaluating those kind of really strong outliers. And it's typically the strong outliers that we really want to get rid of. Most of the other stuff kind of tends to average out some, but those strong outliers we really want to toss, and humans are pretty good at that. Humans are also very good at evaluating, highly elongated stars, double images, significant tracking issues like your mount started slowing partway through a frame or something like that, where the algorithms tend to really fail on these things, right? Double images where you have two stars tend to actually show up as something that looks really good to the computer, right? Those double stars tend to be smaller, and there are more stars in the field, so they tend to be scored higher, right? So things like this tend to skew the results quite a bit. But humans are very good at detecting them. As you're stepping through your images, you can frequently find moving objects like asteroids, comets, alien spacecraft if you come across them. It gives you a way to see the transitory things that are going on in that area of space. Whereas if you're just looking at it with a spreadsheet or something like that, you may miss those things. There are some limitations, though. Humans are best at doing relative compares. So it makes it a little difficult if you're stepping through a bunch of frames saying, was this one better than this one? Do I need to toss this one? You can bring up one of your better frames and then compare things to that side by side, but it's still a little difficult if you have a whole bunch of frames. And you still need some sort of tool to be able to do the visual inspection. You need something that will step through, kind of like PixInsight's blink function, some way to step through all the images and check them. So, automated tools. One of the great benefits is they can handle a whole bunch of images easily, right? You just dump them all in and say, measure all this stuff and report back and tell me what's going on. You can also get an absolute comparison of your data, right? Where it's not a relative thing. It's, this is a star size of 2 arc seconds, straightforward, and so many electrons of charge. You can typically set these things up so they will read back very accurately in absolute terms. Some of the tools can be used for alternate weightings, where you focus on resolution versus signal-to-noise ratio. So you have these really strong benefits for automated tools. They can be tricked, though. Like I was talking about earlier, things like double stars, too few stars in a frame, things like these. It can trick the tool, and they can get off and not report back the correct metrics for frames. Sometimes this can result in false high scores or false low scores, or just false metrics full stop. Different tools report metrics differently, right? So, and they have different weaknesses to some of these problems that we're talking about, right? So you may have one tool that reports everything fine, another one doesn't. So you have to kind of know that these inherent problems exist and try to work around them. Another problem is that most of the tools out there don't run on normalized data. This means that the intensities in all the images match, and that there's no background artifacts or anything like that. It assumes that the backgrounds are perfectly even. So there's assumptions built into these tools that may not necessarily be true, and those can skew the results as well, right? So all these things kind of build limitations into the tools. That doesn't necessarily mean they're not useful. It just means that you have to work around these problems. So I have a small list of tools and their capabilities. These are tools that I've used. There's definitely other tools out there, you can look for, but I'll go through a couple of these here. Fits Image Grader is a pretty, this is from Main Sequence Software, the guys that make SG Pro. It's a pretty simple tool. It uses half flux radius and star count to grade images. It's a pretty reasonable approximation of star size and signal to noise ratio. Typically, the more stars that are found, the higher signal to noise ratio in your image. So it makes a fairly good approximation. You can move the approved images. So if you go through that list and you find some strong outliers, you can, uncheck those and then move everything else to a folder saying, yeah, all this is good. You can't really alter how the score is generated. So you can go through and do your selection and move files, but you can't really alter how the score is created. Deep Sky Stacker is very similar. It uses full width half maximum to measure the star size rather than HFR. Star count and the median or the background value of the image to generate a score. Same here, you can't really alter how the score is generated. You can actually copy the results off to a spreadsheet if you want to do further evaluation with them or things like that, or change the weightings to use in a different program. But you can't really alter how the score is generated and used inside Deep Sky Stacker if that's where you're going to be doing your stacking. PixInsight Subframe Selector. Here you can evaluate full width half maximum, star count, signal to noise ratio, median, noise. There's a whole bunch of star support and other metrics in there. You can generate plots for your metrics. It has very generic weighting and approval equations, so you can be very specific about how things get limited or how the weights are added to be used later in PixInsight for integration. There's flexible star identification and analysis options, so it has PixInsight's star detection, which is part of their registration algorithm in there. So it uses that, so you have flexible options if you have images where stars are much larger than typical or things like that, so you can change those, right? CCD Inspector, very similar to Subframe Selector. You can evaluate full width half maximum, star count, median, contrast, a few other things in there. You can generate plots for various metrics. It doesn't really have a scoring system, but it has an image viewer, so you can look at the images and compare and see whether this really matches it up with what the tool is reporting. It has a few other options in there, for doing collimation and looking at field curvature and things like this as well. AstroPixel processor I hadn't really used until this week, but it does some really nice things. In addition to doing full width half maximum, the star count, signal to noise ratio, things like that for evaluation, even though you can't alter how the score is generated, it does have some advanced features like per pixel normalization, meaning it can even out the backgrounds of all the images and make sure everything is the same intensity before it evaluates things, which is really the holy grail for kind of evaluating data. You really need everything identical in terms of intensities and variation in the background. Like I said, these are just the tools I've used. There's certainly others out there.
David?
Yeah.
One question coming from chat. What is full width half max? I missed it. And
yeah. So
if you don't, maybe I'll add a little bit to it. Can you tell us what difference full width half max and HFR would have for any sort of image metrics?
Yes. So we'll talk about it real quick. So full width half maximum literally means the full width of the star. If you look at a 2D plot of the star, if you take a cross section, you'll see what looks like a normal distribution, a bell curve, right? If you measure the width of that bell curve at half of the maximum, that is what it's reporting. So that is the full width at half the maximum. And that's a measure of the star size, right? Half-flux radius, on the other hand, is measuring the radius of that same curve at half of the flux. Flux is actually an accumulation of all, a sum of all light in that curve, right? So instead of using half the maximum, it's using half the flux. That tends to be higher up than the half maximum is. And because it's a radius, that combination means that the numbers tend to be a bit smaller. They don't directly correlate with full width half maximum, but they tend to track reasonably well. And actually, I have a picture later on showing how these things compare for star size measurement, so we can look and see exactly how that looks, right?
Awesome. That's probably what I want to see.
All right. Any other questions, Adam?
Only Dan commented, Sequence Generator Pro also has an image grader, and yes, I think it's on the top left of David's current slide.
Yeah, there's technically two. So there's the Fitch Image Grader, which is a standalone tool, which is what I have here. And then there's actually their image evaluation. I can't remember what it's called inside the tool. So inside Sequence Generator Pro, it is evaluating things at the same time. It's effectively using the same code that Fitch Image Grader uses, or the other way around. Fitch Image Grader uses the same code that Sequence Generator Pro uses for doing their image evaluation in line with your capture, right?
Now they're proponents of HFR over full width half max, right?
Yes. So the proposition is that half flux radius is more stable to seeing effects than full width half maximum, which is generally true.
Okay.
So for evaluating, data that's coming in from your tool, definitely it's better. For data that's been fully captured, from a long exposure, maybe not. It's hard to say. Typically, the seeing effects are going to be averaged out of the whole frame. So if you're using full frame, full with half maximum, I don't know that it's going to be any less stable. But theoretically, because you're using the flux rather than the maximum, it should be more stable to seeing effects.
Okay. And in SGP, they use that. I'm going to assume most of us use it for focus and then use an outside tool for further evaluation. Basically,
right.
A rough generalization. Is everything going fine? And one more graph on our screen to kind of let us know.
Yeah, and that's a great way. I mean, you're effectively doing your image grading in line with your acquisition, which is a great way to evaluate how things are going and whether you need to change anything. Did my focus slip? Has seeing gotten really bad, or things like that, right?
Yep. And Brandaddy, I think that you're gonna get a better idea of what it is when we see the slides that he's talking about. Brandaddy's asking, okay, full width half maximum, but what does that mean? So I think if you do, I don't know if you have the picture of the bell curve or what you're
I don't have the picture of the bell curve. We can probably bring one up. I may have one somewhere else later on.
All right.
So we might have a better picture of that, but I don't have it in this presentation.
All right. Well, you keep going on your presentation, and then we'll see what we can do for Brandaddy.
Yeah. Okay. So that we define that there are definitely limitations for the automated tools. So we're going to break these down into a few sections and talk a little bit how you might be able to deal with some of these things, right? So if, for example, you take data over multiple nights or from different sites or things like this, you may encounter problems with the automated tools returning metrics that don't really match what you expect, right? So if you have large intensity differences, this can impact the noise, the signal-to-noise ratio, the full width half maximum estimates. If an image is framed differently, it can affect star count and potentially full width half maximum because it's using all the stars in the image. If you suddenly shift the image a little bit, now you've got a big whopping star in there that's being counted. That may really change the picture, right? Or a whole bunch of stars that weren't in the frame before, right? So those sorts of things can shift the results that you get, right? The best solution here is to normalize your data with some sort of form of linear fit prior to doing any kind of evaluation with an automated tool. Unfortunately, a lot of the tools don't do this. I have my little DNA linear fit script that I wrote for PixInsight some time ago, and that can work on non-registered data to give a fairly close approximation of fitting the data. So I tend to use that up front. I will fit the data first, and then do the evaluation on it. Right. That way, you get something that's pretty close to the same intensity range, which really helps with things like noise evaluation and star sizes. Because if the scale is different between your data, it can really impact how the metrics come back. If you do have significant signal-to-noise ratio differences in your data, it may be better to actually make small stacks of the low signal-to-noise ratio data, and then combine those as individual subs along with the high signal-to-noise ratio data. So, for example, I took 10 frames from a dark site, and then I came home. They were all 10 minutes or something like that, and I came home and I took 90 images from my light polluted area. I might take stacks of 8 of those, combine those, register, combine, do everything I need to do, and then treat those as a single sub in my larger stack, right? That way, the signal-to-noise ratio in that sub is a little bit closer to what the other dark frame subs are going to be. So when you combine everything together, it does a better job of weighting and making sure that the result is closer. That's one way you can get around some of the limitations. Sometimes the low signal-to-noise ratio data is so much lower than the dark skies data, for example, that there's no real point in using the low signal-to-noise ratio. It's only ever going to degrade your images. But these sorts of tricks can sometimes help. Sometimes your results don't match with your visual observations, right? So if you've done, step through all your images, and then you're looking at the results and saying, well, this doesn't really make sense to what I saw, right? You can have some of these types of issues, right? So sometimes if there are insufficient number of stars in the frame, the metrics may not be calculated correctly for star size, for example. There's significant noise differences, like we talked about, due to light pollution, the moon being up. Maybe there's thin clouds reducing transparency. That can affect your signal-to-noise ratio, which affects the results. Double images we talked about before. If there's a tracking problem, and each star is represented twice or more in a single image, this can really throw things off. Comparing those things, or comparing, with different filters, like if you have HA data in with your luminance data, those things don't compare very well because the star sizes are so much different relative to the signal in the image. They don't really compare well. So you may go through and step through all these things and say, oh, this looks great, but this is reporting, it looks terrible, right? Median's too high, it's not scoring it well because it doesn't have enough stars in your data or things like this, right? So trying to limit those things, if you're doing different filters, try to do them, in sets, all the same filters, or at least separate out your narrowband and broadband data, right? If you have all these other issues with different signal-to-noise ratio differences, try doing some of the things we talked about before, like making small stacks from your light polluted data. If you have too few stars in the frame, sometimes the tools are just not going to work, right? They kind of need a certain number of stars. Various tools need different amounts to work appropriately. So generally, I do a passive visual inspection before and frequently after running an automated tool to verify that everything matches up with what I expect. If that's not the case after all those passes, then I need to go back and try something else, right? And sometimes you end up with frames where the tool will simply not correctly detect the metrics, right? It's just never going to give you the correct result. You're hitting a case where it just can't work properly. And in these cases, if it's just one frame or two frames, typically what I'll do is override the results manually. If I'm doing image selection, I'll either toggle it on or off, make sure I copy that file over with everything else if that's what I need to do. Or if I'm weighting the data and this weight is just really high or really low, I'll go in and modify the fits header and make sure that the weighting value gets updated correctly for what I expect, right? So sometimes, the tool's just not going to give you what you want, and you have to manually intervene. And like we said, sometimes metrics don't match between tools, right? They measure data differently. And so there will definitely be inconsistencies. The tools also have different feelings. So sometimes, you'll get wildly different results from one tool versus another. So on the right here, you can see a picture of star sizes measured in 4 different tools. So the orange line is subframe selector. The gray line is CCD inspector. The blue line is FITS image grader, and the pink line, purple line there is deep sky stacker. And you can see a few things pretty quickly, all right? CCD inspector reported this image and this image with a really low small stars, right? So these things would actually be scored really high because the stars were so small. But in reality, they weren't really that much smaller than anything else. Maybe in this case, they were a little bit smaller, but not significantly so. So, these happen to be because there were not enough stars in these images for CCD inspector to work correctly, and so it kind of failed. It just didn't understand how to deal with these, right? You can see most of the others kind of track along. When things get really bad, they all detect that it's really bad. Or really good, except in this particular case, you can see CCD inspector went the other direction. Most likely here, it's tossing all the really big stars, so it didn't include them and just looked at a couple others. It may be finding some hot pixels or something and saying, hey, this is great. The other ones seem to track pretty well. The orange and the gray kind of track a little bit lower than the blue and the pink here. The others track okay. These don't come up as much. The blue and the pink don't quite come up as high here. So the subframe selector and CCD inspector seem to have a little higher variance than FITS image grader and DSS. They seem to track pretty closely. The FITS image grader, like we talked about, is using HFR. You can see I've made a note here. What I've done is scale these. So in reality, the FITS image grader numbers were not quite half. They would have been sitting down here. I've scaled everything up to the same median value for all star sizes so that they could sit kind of on top of each other and you could better compare how they differed. But in reality, this blue line would be sitting down here, and it would be tracking with these things reasonably well, but it would be lower, and that's normal, right? All right. Any other questions yet, Adam?
No new questions. Brandaddy, I did get that bell curve, so we'll pull it up when he's finished with his presentation. Or when it's appropriate, David.
Yeah, why don't we go ahead and pull it up now, Adam?
Okay. It is on my screen, so you should be able to see it if you see me.
Let me switch over to you. All right, so what Adam has here is effectively a star profile. It's a normal distribution, kind of like what we see is a bell curve, right? The full width half maximum you can see written right here. Effectively, what they're doing is they're measuring the width of the star at half the maximum value. So they measure the peak. They say, okay, I'm coming down in Y, half of that value, and then I measure the width of the dispersion of that star at that point. So that's how they're getting their star size measurement. The half flux radius is different. It measures just the radius. So this sigma value here is probably a little closer to what half flux radius would represent. It may be a little higher up because most of the flux is actually centered in the very center peak of the star. Most of the energy is very, very high up here. This normal distribution is not like a typical star. Most of the energy is very, very peaked. So most of the energy is here, or the flux is in the very center part. So the half flux radius tends to be pretty high up, and then it's only measuring the radius. So you can see this width is going to be a lot greater than this width. But they should track fairly closely. And you can see in my presentation, that's generally true, that these things track pretty closely here. Did we answer Granddaddy's question with that slide?
I think we did. Brandaddy, tell us if we didn't, and otherwise, Dave, keep going, and I'll let you know what he says.
All right. And of course, you know, what do you do if these metrics don't match up between tools you're looking at? If you have access to multiple tools, it can actually be a big advantage, because you can see areas where one tool has problems and another tool may not, right? So it may actually help you evaluate problems with other tools. One has a failing that the other doesn't. You can get around that by using another tool. I always compare my calculated metrics with visual observation. That way I'm guaranteed that I know exactly what I'm seeing. I'll have a spreadsheet up or something and saying, this doesn't look quite right. You know, it reported this, but that doesn't really match up with what I'm seeing here. Again, you know, these frames that have low signal to noise ratio or double images, lots of hot pixels, things like that, these tend to be the ones that cause issues. At certain points, you know, the tools are just never going to work for those some of those things, and you'll have to deal with those things manually, right? You know, visual inspection, manual intervention are frequently, for the real trouble frames, the only choice you have, right? So if you really want to focus on these sorts of problems, you know, that's what you tend to have to go to. Okay, so these are kind of final words for the presentation part, and then I'll get into a demonstration piece here. One of the things I noted is that in putting this presentation together, I really struggled to find any of my recent data sets where tossing frames made a significant difference. That's generally just because my data is coming from the same site. It's all fairly consistent. I'm not taking data when the moon's up with, you know, broadband. So it tends to be pretty similar, and tossing frames doesn't make that much a difference. Maybe one night I get seeing this a little worse than another night, but averaging together kind of mitigates that, right? So I can spend a lot of time sometimes on evaluating these things, and sometimes not end up with much of a difference. Maybe it's 1 or 2% gain or something like that. Sometimes, like I said, as much as 10, but it's pretty rare when I see that much of a difference in my own data. It's working to get that last 5% effectively is what I'm doing, right? You know, dropping a few bad frames or adjusting the weighting, you know, frequently saw small improvements or trade-offs in most of my recent data. I had to go back quite a few years where, you know, this started to make bigger differences in my own data sets, you know, where I was having a lot of tracking issues or things like that. That's where it really starts to pay off more. Or, you know, it's actually very beneficial for collaboration projects. There it really makes a difference. But, you know, in my own data where it's all the same equipment, it's not a big difference typically. You know, this averaging, the pixel rejection algorithms we have access to, they typically take care of 90% of the issues that we encounter. And frequently you won't even see a visual difference. You know, you can measure something, you know, where, yeah, in this image, the star sizes are, you know, 2% smaller, 5% smaller. You know, run signal to noise ratio, you know, a few percent. But it's kind of, again, making out those small differences. They can, you know, result in a little more benefit in the end, but, you know, it's up to you whether you want to spend that time trying to get that last 5% or not.
David, can I make a comment?
Sure.
I just wanted to comment that when a lot of the guys on the Astroimaging channel do collaborations, we tend to dump a whole lot of data on David's desk, so to speak. And he's the one that tends, that really does a good job of exactly this. And I think, David, when you say it makes very little difference, I think that's going to be most of the data we come across. It makes very little difference. But with the collaborations, it does make a massive difference.
Yeah. Collaborations, if you have a lot of variance, I said this up front in the presentation, if you have a lot of variance in your data, or you have, significant tracking issues that you're dealing with, things like that, that's where this sort of thing pays off. But if your data is pretty consistent, you're hammering out your data every time, it's not going to make a lot of difference. And it's really up to you whether you spend that time trying to get that last 5% or so, right?
Right. And trying to eke 5% out of, I'll say, half a gigabyte of data is pretty tough, right?
Well, it's right. It can really add up in time.
It takes a long time.
Yeah.
All right. Well, I just want to point that out.
Yeah. Okay. So let's jump into a slight demonstration here. I'm not going to go into a huge amount of detail, but I'll go through a couple things kind of about my philosophy, where I would make the cut and things like this. So I have a particular data set here, and I'll kind of step through this. So I'll try not to blink back and forth too much. I know YouTube doesn't really like that, so I'll try to stay on an image and let it stabilize a little bit. So what I've done here is I have the blink tool up in PixInsight, and I'm going to kind of step through these and visually select them, right, and determine whether I want to keep that frame or not, right. So this first one, just visually looking at it, the stars kind of start to almost look comet shaped. They have a peak over here and are kind of flat on this edge. They don't look really good, right? And then when I compare it to this one, the stars are significantly rounder, right? It's much, much cleaner stars. They're much more focused. But at the same time, I lost a lot of signal to noise ratio. This image is not nearly as clear as this one in terms of depth, right? So you have to kind of make a trade-off. Do I want to focus on how deep I'm going in the field, or do I want to focus on signal, on resolution? In this case, I have a fair amount of data. I have, I can't remember how many frames this was, 108 or something like that. 15-minute frames taken over multiple nights from a dark site, right? So, in this particular case, no, it's not 108. It's 55, I think, right? So, quite a lot. In this case, I want to focus on resolution, so I'd end up tossing this guy. Those are starting to look like seagull-shaped stars. I don't really like those. I'm going to toss that frame. And then I kind of step through the images, and I can clearly see from this one to this one, there's a step up in star size. Not a lot of change in signal to noise ratio. They both look about the same intensities and clarity in terms of depth. So I would keep this one. I might keep going through my list and see if they get any worse. And yeah, they're really starting to get bad there, even worse. And then they're better again, right? So this was a session where I had focusing problems, where the focus kept slipping. The draw tube was slipping, right? So I'd probably end up tossing a couple of those frames. I might keep this one. Stars are starting to bloat a little bit, but that one's probably going to even out some. And so I'll just kind of go through, if at the end I've tossed too many, I may go back through and reselect a few things. This one looks a little bad, but probably not that much worse than this one. Yeah, they look about the same. So I'll keep that one too. You can see this one, probably about the same star sizes, but the signal to noise ratio is much worse in this one. And it's better again. Is it worse, bad enough that I'm going to toss it? Probably not. I'll probably keep that one. So I kind of keep doing this, and you can see here, the focus really starts to shift. You can see I unchecked this one. This one's really, really bad. So I'll turn that one off. And I'll just keep going through there. So this one, not terrible. I'll keep that. These are getting worse again. I might uncheck that one, turn that one off. And so I'll just do this for the whole list. some variance in there. But if they're really bad, then I tend to toss them. And really bad is typically, it's visually ugly, right? You know, those stars do not look pretty. I'll probably turn that one off. Same with this one. They're starting to look like seagulls. Maybe, yes, that one's quite a bit worse. So, yeah, so I'll probably keep this. So then I'll look and say, okay, well, I turned off 1, 2, 3, 4, 5, 6, 7, 8. I turned off 8 out of 55. That's not terrible. I might go back through and look at a few of these and say, well, that one's pretty bad. This one's not quite so bad. This one's not quite so bad. That one's terrible. This one's not so bad. Maybe I'll turn this one back on. This one's not quite so bad. That one's pretty bad. So, yeah, maybe I'll do that. And 1, 2, 3, 4, 5, 6. So that's about 10% of my images that I disabled. And then once I've done my visual inspection, I'll go through and select everything. So let's select these guys. Don't know why I didn't select everything, but okay, so that's everything selected, and then I would move these, or copy them in this case, to a result. So I would copy them off to a visually approved directory, right? And then I would take that and bring it into subframe selector, right? So we'll close Blink real quick. I'll bring up subframe selector. So subframe selector had my specific frames in there. I'm going to go ahead and get this started in the background. While that's running, Adam, do we have any other questions?
Yes. Excuse me. Yes. Can you use the tools to create different stacks and then compare the stacks against one another to figure out what the best one is, data-wise, not just visually?
Can you use the tool to create different stacks and then compare the stacks against each other numerically, right?
Yeah. So I think if you're
maybe not in an automated fashion, right?
Right. Right.
So for example, you can move data into different directories. You can, what you might do is a first pass of subframe selector, and then group things based off that information. Go off, register them, stack them, and then you would take those stacks and effectively use them as subframes, right? That's kind of what I was suggesting for dealing with big changes in light pollution or signal to noise ratio in the images, where you have a few frames that are really good quality, and then you have other frames that are not so good. And generally, what I would do is, like these are 15-minute frames. My light pollution frames are going to be, a tenth of that. They're probably 90 seconds, right? You're just never going to capture the same signal to noise ratio in a 90-second frame from a light polluted area. But if I take 30 of those, and combine them in one stack, and then take another 30, combine them in another stack, not worry about, what's grouped in each stack, just kind of lump them together. And I may do some testing to see what the signal to noise ratio is in those resultant frames and see if they're approximately equal to what's in the 15-minute subs from the dark site. Then I would kind of regroup things a little bit that way. And then those would end up as being a couple additional frames in my entire stack. I don't know that there's anything that does the kind of grouping that he's talking about automatically, though. I think you'd have to do that manually in some way.
Okay, thank you.
All right, we're only through 25 out of 55 subs. Any other questions?
No other questions. I did, let me check what that was in the room. Sal, We actually use the chat tool on our website that breaks away, but you can use this one, and if you want to ask questions, you're fine to type them in here. I'll still see them. But we don't use YouTube chat, so stay off YouTube chat. It's just difficult to keep that open while the other chats are open for a few different reasons.
While this is working, I'll go ahead and bring up. So let me bring up Fit's image grader. Let's see, I put that on here somewhere. So Fit's image grader is pretty straightforward. I'll just add a couple files in here just so you can see what it's doing. Oh, didn't like that. That's something you don't want during a demonstration. It crashed. Let's see if we can try this again. Nope. That's really interesting.
David, are you trying to grade the same subs that PixInsight has open?
No, it shouldn't be. I have a separate set of FITS files. I converted everything to 16-bit FITS to make sure that it could pick them up.
Gotcha.
So I'm not sure why that's doing that. It wasn't doing that earlier, so maybe I'll figure out what's going on there. But regardless, what it does is it loads in. You know, you add some files or add folders and tell it to include subfolders, things like this, and it goes through, loads them all in. It doesn't do everything initially. You have to click the grade button, and then it goes through and uses effectively the same half-flux radius and star counts that SG Pro uses for their analysis inside. It's made by the same people, right? And you can go through and you know, it'll report these things in a column. You can check or uncheck them, copy them somewhere if you choose to, or you can, you know, write the data out as a comma separated lists file, right? So you can bring it into a spreadsheet and copy it out if you want to, right? So it's a very simple little tool, but it actually works quite well. It does have a few limitations. Like I said, I'm not sure why it's crashing at the moment, but all right, so subframe selector is now up and has measured everything. Because this is a JavaScript app, it's kind of slow and it takes over the session, right? So you can't do anything else in PixInsight while you're doing it. That's a limitation. It's not multi-threaded or anything like that. It's effectively running Java under the covers. So, you know, I've got my system parameters in here for this data. You can set all the star detection information in here. And then here is where you do like approval settings. Like here you can say, I'm looking for only allowing images to be approved if their full width half maximum is under 3.4, which is pretty sizable for my typical data. That's pretty large. And I'm looking for the signal to noise ratio weight to be over 1.5. So let's take a look at what these look like. So, so this is the full width half maximum plot. So at the bottom we just have the index of the frame, and then you have the star sizes and full width half maximum in arc seconds on the left, right? Now you can see there's clearly some strong outliers. You know, these are kind of, this one and this one, they're getting strong, but I don't want to exclude too much. So I left these in here. You can see there's a couple other frames that are being excluded even though their full width half maximum is not that high. And that's likely because their signal to noise ratio is very low. So if I look at that, you can see, yep, those two frames are pretty poor in terms of their signal to noise ratio. In this case, signal to noise ratio is better the higher the number. Full width half maximum is better the lower the number. Right, so keep those things in mind as you're doing your weighting. You can see I'm using a very, very simple weighting system here. It's simply, you know, signal to noise ratio weight divided by full width half maximum. Since this is better the higher the number, I want it proportional to the weighting. And because this is better the lower number, I want it inversely proportional to the weighting. which is why it's on the divisor, right? So, you know, this is a very simple weighting algorithm that's pretty much absolute for any kind of data set. You know, if you're using your own camera and everything like that, it's pretty straightforward. I have some more complex ones. Some of you may seen before. I have this spreadsheet. It's published out there. I think it shows up in Warren's book and a few other places for PixInsight on different weighting algorithms. And you can go through and put things in here and change the weighting, focusing on star size or things like that, right? So, but ultimately what we're trying to do here is you know, use this information to evaluate whether you want to keep a frame or not, and potentially weight the frame for a combination later on. And so you'll do whatever you want to do here, and then in this case, I'm going to, you know, write everything out, copy it, not move it to an approved directory. It's going to append an _A on there, and then the weighting value is going to be created with this SFS weight subframe selector weight that gets stuck in the fits header, which image integration can use later on. CCD inspector works very similarly. Bring that up. You know, you just add some frames in, and then click measure all, and it goes through, and so I'll just click on a few here. You know, I have a default image scale in here. I'll just use that. It's actually not correct for this particular equipment, but that's okay. It's still going to give me some absolute values. And it goes through and measures. It reports the full width half maximum. And you can change what the columns are: contrast ratio, background, aspect, which is the eccentricity of the star, number of stars used. So it can use that information. You can, you know, copy this stuff off. So I can't remember where this is generated. I think you can just, let's see. Can't remember if you can just copy it. I know you can just take this data off and put it in a spreadsheet. Let's see if I can just copy it out. Nope, I don't remember offhand. But at any rate, you can copy this data off and put it in a spreadsheet and change it. If you want to use that information to create weights or something like that that you can apply later, you can do that sort of thing here too. But ultimately, it's giving you the same type of information: full width half maximum, aspect ratio, background values, number of stars, that sort of thing. I'll leave that up. And then Deep Sky Stacker is the last one. You know, its tool is really used for really intended to be used by its internal processes. You know, you have to kind of register things to get them scored. And then once you do that, this information can also be copied out. I think, you know, this is, yeah, this one allows you to copy it to clipboard and paste it in. So you can get all that data and dump it into a spreadsheet for you to use later on, right? So you can do the same sort of thing, dump it in a spreadsheet, do some more calculations on it if you want, or you can just use the scores as they're generated in there. It also has a viewer, right? So you can, you know, stretch your data in here and make it a little easier to see so that it's back this off a little bit. So you can kind of visually inspect things a little bit. So now you can step through your images. Takes a little while to upload and see what's what, you know, if they're reporting what you think they should be and that sort of thing, right? So it gives you both a visual inspector and numeric calculation at the same time, which is nice.
David, a few questions popped up.
Sure.
The first one is from NoCloud, who was the one who asked the question, you can use the tools to create different stacks and then compare the stacks, etc., to find out which one is the best one. And his follow-up question to that is, so you're saying that the tools can look at each sub and make determinations of how it will handle that sub prior to stacking.
Well, actually, thinking about his question, he may be asking something slightly different, which is he may be asking, can you combine all the data into different stacks and then evaluate the stacks, you know, completely stacks, all frames included or tossed or whatever you want to do. That may be what he's asking, in which case, yes, you can change the weightings and you can change what gets included or not included and restack those sorts of things. There's still no real kind of automated way, partially. You could potentially take each of those stacks and treat them as a subframe. You can put them back in the subframe selector and look at the star sizes and signal to noise ratio. That might get you some information. I've never actually tried it that way. I tend to only have a few at a time from a completed stack. So I'll do a few different variations and compare them. But then I tend to do, you know, manual comparisons where if I have two images up, let me bring up something here. We'll just pretend that these are stacks, right? Once I've done all my stacking and everything, I tend to keep the images up, and then I'll use targeted selection, like I'll use dynamic PSF and measure specific stars. So I might measure a few stars here and do the same thing on this one. So that's these 3 stars here. And then actually look at the results here and say, you know, these guys are 2.5, 2.06, full width half maximum. These are 2.95, 2.54. They're quite a bit higher. So, you know, I would say that first image is better in terms of resolution, right? So I may make some qualified statements like that. I tend to also just, you know, I'll measure the background. I tend to do this on registered data, so, you know, it's on the complete stack, so there'll be exact matches of the same area of background. And I'll look at the statistics, making sure everything is normalized and everything in the data. Actually, I'll do this by telling it to track. So if I look at this one and measure the standard deviation here versus here. So this one, the standard deviation is 0.1747. This one is 0.1784. So this is a little bit worse. So my stars were much better, but signal to noise ratio is a little bit worse. So I would say this was the better result type of thing, right? So you should be able to do that to a certain extent with like subframe selector or CCD inspector. You need to make sure that the data is normalized beforehand to make sure your results are correct. Normalized meaning that the intensities match between the frames. But you should be able to do that, yes. And what was the other question?
Let me go to his third follow-up question. Yes, I was wondering if I could stack my good images and then add some of the discarded ones back and see how they affect the stack data-wise.
Yes, absolutely, you can do that. You know, in fact, you know, for some of these comparisons, like, you know, in the presentation, you see things like this, right? So this is just a visual comparison, but it's effectively doing the same thing. I've made 2 different stacks, one with everything included, one with some frames tossed, right? And here we're just looking at them visually. But you can certainly put those things in subframe selector and see what results it gives you. It should, in this case, tell you that your signal to noise ratio weight is better and the one with all the frames included, but your full width maximum is worse, all right? So you can definitely do those sorts of evaluations.
The next question is, how do you know when too much data is too much data?
I don't know there is such a thing as too much data, really. There are always points of where it's diminishing returns, right? That's a difficult question to answer. Generally, if I'm not seeing a lot of, I'll take data over multiple nights, right? So my projects tend to be in the 20 to 40 hour range for a single image. Generally, if I'm not seeing a lot of improvement on the third or fourth imaging session, then I might go ahead and call it, right? Unless the image is just not where I want it to be. So, I'm still sharing my screen, right? You can see this picture of M101 in the background, right? That image isn't where I want it yet. So that is just a sample of what I've collected so far, but it's not as deep as I want to go. So I will be collecting more data on it to go further. Now, it may actually already be too late to get that this year, but so that'll come around next year, and I'll collect more data and add to that, right?
Adam?
Yes.
Adam, I wrote a short article on when is enough data enough.
Yep.
That was published in the SRO newsletter. I'd be happy to kind of excerpt that and share it if anyone were interested, because it addresses just that question. When is enough data enough? When do you stop collecting? And using analytics to figure that out.
Yeah.
Great.
So there will be diminishing returns. Definitely, yeah, I'd like to, I don't know that I've read that from you, Eric. I'd like to see that.
Are any tools better at identifying subs with satellites or airplanes crossing the field?
None of the tools are really good for that. Most of them, they're very specifically looking for stars, right? So they tend to not, a satellite trail or airplane tends to look like a very thin line, and so they tend not to include those. So I don't know of any tools that really identify that, or comets or things like that, or asteroids. The tools don't tend to handle those at all. So generally, visual inspection is what handles those. If you have enough frames, rejection tends to deal with those perfectly well, though. You do need 15, 20 frames to really make it work appropriately without tossing a lot of data to reject them statistically. But statistics can get rid of them without having to deal with anything else, and you lose almost no signal to noise ratio in the process that way.
And you are all caught up on the questions.
All right, that's it for my presentation. So if there's
Eric, did you want to touch on that right now? Eric, did you hear me or no? Can you guys hear me?
I'm sorry, I had turned off my mic.
Oh, no problem.
It's a little difficult just to get in just 30 seconds, but the elevator pitch for the idea is you keep on accumulating, like say for an LRGB image, the L image, which gives you your detail, stacking it up on sequential night, doing the analysis of the SNR and other values on those sequential images, and eventually those things will plateau, and that's about the point that you quit. And whether it's 2 days, 3 days, 4 days, or 5 days, you just come to a point where it's enough. You can always go on indefinitely, but they have a limited amount of imaging time, so you have to decide when to stop.
Right. And if I'm going to assume that we all kind of do the same thing. You get your first night's data, and you're so excited. Well, I shouldn't even say that. Maybe you get your second night's data, and you're so excited about the target, you stack it, right? And then you decide you want a little bit more out of it. So you take a third night's data, and you stack it, and you look at it, and you evaluate it, and you decide whether you want another night out of it. But the key point that I heard both Eric and David say is, I think Eric said plateau, and David said diminishing returns. And that's really what you're looking at. And the point where you stop isn't some firm, you must stop here. It's when is it good enough for you? And
but it's reducing it to analytics rather than just visual, like I've had it with this image, I'm moving on.
right, right. But you also, when you reduce it to analytics, right, you can double the amount of time to reduce the SNR. But when that reduction of SNR becomes an inconsequential amount, then you're at that point, right? So, yeah. But it's the same process, and it's seemingly a similar way of figuring it out. But I think what David's given you tonight are a lot of just good, whether it's tools or keywords to look at within those tools to basically improve your pre-stack data set to give you a better stack.
Yeah, and like I said, you know, there are diminishing returns in how much effort, you know, how much result you get from efforts like these, right? So keep that in mind. You know, if you're that type of person where spending a bunch of time doing this is just going to infuriate you, don't worry about it, right? Just go along and stack everything. For the most part, rejection and law of averages is going to work things out, right? So, you know, unless you're actually frustrated with the results you're getting, you're seeing lots of weird star shapes, but you know you had some good data in there that wasn't like that. You know, not pruning your data is not going to affect you too much, right? So there has to be pretty severe problems before the pruning data and you know, weighting data start to give pretty big benefits.
Glenn, you're asking if I don't know if it's me or everyone else stack each day or put it all together. And no, I do stack it all together, but sometimes as I'm in the process of taking the image, I'll stack the first night, then I'll stack the first and second night, then I'll stack the first, second, and third night to just see how the increase in the amount of data I have improves.
I think, yeah, Adam, Eric, and I are saying all the same thing. I think all of us kind of do that, where we are accumulating data, and you know, I tend to stack everything I have after a session, right, and see how it's progressing. Is it, you know, looking to be enough for what I want? How much additional time am I going to have to spend to improve it? So you know, there's definitely a progression there. I will try to estimate, you know, this is really, I really want more out of this. How much time am I going to put into this if I really want to get this much further? It's going to be another 40 hours, right? So that seems unachievable. So I will, you know, make calls like that as I'm going through session by session. You know, there are other advantages to taking more data besides just, you know, what's included in the stacks, because, you know, we're talking about, you know, rejecting images and things like this and weighting images. It gives you more flexibility. If you take more data, you have more flexibility to what can be excluded, right? Because you have more total frames, right? So you can be more selective about your data as well, right? So there are other advantages besides just the total accumulation of time.
You know, another point to add to this is that when is enough data enough really only applies to your LDIM image and an LRGB image and to the HA image in a narrow band. And those are the ones where you want to push it to whatever limits that you set for yourself, especially if you do tone mapping.
Glenn's asking, what about darks, flats, etc.? And with just when it comes to darks, flat, well, when it comes to calibration frames, we're all calibrating our images. Some of us may not be taking darks. We might be dealing with that a different way. I think David uses bad pixel maps. I use darks. Some people don't use darks. Darks are, I hate to say it this way, but probably the least important calibration frames, or they make probably the minimal change in calibration, but that's kind of a separate process than the evaluation of the data.
Yeah, I would say that darks can be really important depending on your camera. if you're using like one of the ASI 1600s where they have strong glows and things like that in there, the darks can actually be really important for those. Because those glows build up very quickly as signal if they're not removed, and can really affect how flats are calibrated. The flats won't necessarily apply correctly if that pedestal, which is variant across the frame, is not removed appropriately. So there are reasons why flats are important. You know, the only reason why, darks are important. The only reasons I wouldn't do darks, and is if you have a thermally regulated camera. A DSLR or just a camera that the cooler is always on 100%, then I wouldn't worry about darks. I would deal with that all just through averaging out. But in all other cases, darks are definitely important.
Thank you. I actually hadn't thought about any sort of glow, or hadn't considered that, but that's a good point. That is it. No more questions. Our next week's episode is on the CATE project, going to be presented by Burton Briggs. Basically, it is, you'll hear more about it next week, but it's a project to track the solar eclipse from a large number of different sites through the country, and to try and get a continuous view of it. Which is going to be a pretty impressive feat, and it's going to be a pretty impressive event. I can't wait to see the results of this, but we're going to hear a lot about what's going into the project next weekend. I want to thank David for presenting another great presentation, and I want to thank all you guys for asking your questions and basically just signing in and seeing what's up. And if no one in the room has anything else to say, I'm going to sign us off. I don't see anything new popping up on the left or on the right. So thank you guys. Just a quick, okay. Thank you guys. We will see you all next week.